It's a pleasure, many said it before, to be here at this conference. And to express my thanks to the organizers, I will not be talking only on spherical splines, but on a little bit more, and therefore I extend the title of my talk to supraspherical splines. But if this raises your expectations, I will ground them by adding this subtitle, telling that everything boils down or is based on well-known techniques. I said I ground your expectations, and here we are at sea level, so we start at the very bottom. I'm using boldface letters to denote vectors here in R3, or multi-indices of 3 non-negative integers summing to n. They define the Bernstein polynomials, but different than usual, we do not restrict them to the plane where the 3 parameters sum to 1, but consider them over all R3. So these are homogeneous Bernstein polynomials. With this basis transformation by this matrix A, we consider then polynomials, homogeneous polynomials in X, which have then a unique Bézier representation. This is homogeneous, so we get here a homogeneous Bézier form with respect to this matrix A. And if we restricted everything, the 3 basis vectors define this triangle. If we restrict the polynomial and the Bernstein polynomials to the triangle or the plane of it, we obtain the standard Bézier form. Both have the same Bézier points. Now, we will see that we need to change the matrix by scaling the basis vectors, so going to a different triangle. These factors, they go just through to the Bernstein, to the Bézier points, and so changing the matrix by scaling that, we obtain new Bézier points that are just multiplied by powers of the scaling factors. Well, now if we restrict such a homogeneous polynomial to the sphere, we get what Alfred et al. Called the spherical polynomial. And if we multiplied the unit vectors by the values of a homogeneous polynomial or spherical polynomial, we get what they call a spherical patch or spherical Bernstein-Bézier patch. And of course, we can take pieces of these and piece them together to get a spherical polynomial spline. And if we extended it homogeneously, we get a piecewise homogeneous polynomial spline living then on R3. And this can be restricted again, but now to a plane, to get a bivariate spline over some plane. And this tells us constructing a spherical polynomial spline is nothing else than constructing a bivariate spline. All of them, all of 3 things, have the same Bézier points, they don't change. But there's only one thing: if I have a sphere, and consider now a plane, and say I had some triangle here, and consider the Bézier representation over it. I have this cone, where I consider this homogeneous polynomial that goes with it. And then I see that the plane only covers half the sphere, a hemisphere. So I need several planes to cover it. And going now from this Bézier representation over this plane to that plane is easy, as we have seen. And so we can construct a bivariate spline, continue on another plane, and finally cover the complete sphere to get a spherical polynomial spline. Now here you see 2 examples, a Dam-Micheli-Seidel spline, spherical spline, and a Paul-Sevin spline. And what you see in the upper picture is a control net. But This is not a usual control net with a usual geometric meaning. This is just a visualization of the scalar control points over the sphere and has no geometric meaning, at least no direct geometric meaning. If we wanted to get out of it, we need to do a little bit more. So in general, we have that over the sphere for the spherical polynomials, patches and so on, we have no Bézier net as we are used to. But what we can do is take a spherical patch, extend it by a coordinate. So we have here 4 coordinates now. And since the variable is a unit vector, this is the norm of it. So we can write it a little bit different. Take the norm and take it to the power d plus 1. This is here for an odd degree polynomial, so this is a polynomial 2. And what we see here, all the coordinates are homogeneous polynomials of the same degree. So what we really get here is an homogeneous representation of that spherical patch. And we can inhomogenize it again by dividing through the last coordinate, and we get a rational polynomial living here on the elliptic plane on S2 or the projective plane. And this one has a rational Bézier net with the usual geometric meaning. Here you see examples. These are piecewise cubic splines, then represented by quartic polynomials. And here you see the Bézier net. This one is also the Bézier net, and here also you see the Bézier net to it. These things are special rational patches on the sphere, and before I do this, I come to that. Just explain this briefly. There's a nice relationship between the spherical representation and this rational representation. Say this is a cubic polynomial, it works for any higher odd degree, and then we have this quartic representation. Here are the Bézier points, and they are related in the following way. I depict this quartic Bézier net again here on the right side schematically, and then I put the Bézier coefficients here into the upright triangles in the natural order. Now, if I change one of these Bézier coefficients, say this one here, it only affects the 3 next Bézier points next to it. In the following way, these points are moved along the directions pointing to the corners of the patch. So the Bézier coefficients are certain design parameters we have here on that Bézier net. Now, these are special rational patches, and I would like to consider general rational spherical patches. So I repeat it again here for an arbitrary 4th coordinate. This is a polynomial then again. This is an homogeneous polynomial. And we have here a vector in R4. I'm using here hollow letters to denote that because these are homogeneous coordinates. And they represent this rational polynomial going into R3 then over the sphere. And for that one, there is this Bézier net. Since these are homogeneous coordinates, they are only determined by a factor. And this factor is the weight that goes into here and is needed to define that this surface. But it's good to depict these weights by these weight points, which we get if we take here 3 points of such a triangle and adding the homogeneous coordinates. This gives us the homogeneous coordinates of the weight points you see here. And the weight points, together with the Bézier points, they define the rational patch. And the advantage of using these points is that this representation in these points is projectively invariant, whereas if we had here only the weights, they are not projectively invariant. Now again, if we changed the reference triangle, or here this reference matrix, by scaling it, what happens, only the weights are changed of the Bézier points, and that means only the weight points change, but the Bézier points stay the same. This, by the way, means that we reparameterize a patch by a special projective map that maps the triangle onto itself. Now, we want spherical splines, and therefore I put together polynomial patches, and doing it for the homogeneous representations, or we have these polynomials in R4, which are integral polynomials. I can use this well-known condition how to construct the next polynomial that has a CK joint. Certain quadrilaterals formed by the Bézier nets need to be affine images of the domain triangles. And now this lives in R4, and if we inhomogenize that to get a rational patch, we have a projective transformation of it. And this then leads to the projective version of this condition. If you have two rational polynomials, then they have a CK joint if these quadrilaterals, which I call C quads here, are projective images of each other or of the domain triangles. Of course, we should not forget the weight points here. Otherwise, it's clear that any two quadrilaterals are projective images of each other. So if we didn't know the domain triangle, we could get one just by any projective transformation. And what is interesting, or the only thing we really need to know for this CK joint, is how this triangle is related to that other one. So the map that maps from that triangle to that one, this transition map, defines the CK joint we have here. So the transition maps will be important later on. Here I depict part of a Bézier net of a spline, of a smooth spline, so it's at least C1. And we see here the Bézier nets at the corners of a patch and the configurations around that. Now here's a C quad, and this one is a C quad, and they are related then, these are projective images by a projective map, pi2 here. And similarly for all the other boundaries we have here, so we have three projective maps, and going around, this triangle then gets mapped to that, to here, and back again to here. We should get the same triangle, which means that these three projective maps should be the identity. This is what I call the compatibility condition. And if this is satisfied, we basically have a spherical spline, smooth spherical spline. And constructing a spherical spline, well, I said we could go to bivariate splines and get it from there, but here we have a different construction. Can be done as follows. First, we choose a patch layout. Second, and also we could choose a candidate Bézier net, say of a C0 spline. Then we move the Bézier points so as to satisfy the compatibility constraints. And once we have done that, and then also satisfy the CK constraints, we are done. This is all we really need to do. And from that Bézier net and the C quads we have there, we obtain also the transition maps. And if we picked one parameter triangle, we get the adjacent parameter triangles by the transition maps. And so we would get the complete triangulation of the sphere. And having that triangulation of the sphere, we can then construct any other spherical spline using these transition functions. Now, computing this is, of course, a nonlinear optimization we have here, and we get other talks tomorrow by Carolina. She will explain how she is doing it. There are several possibilities. Either if we go back here, if we start from some Bézier net, we had here three projective maps. In general, they would not compose to the identity, but then we can optimize these projective maps to be close to the ones we have here and to satisfy the compatibility conditions. And once we have that, we yeah, this one way, or the other way is we can choose parameter triangles arbitrarily and use projective maps that map here to the Bézier net and try to find projective maps that give us a Bézier net which satisfies the compatibility constraints and is close to the first one we have given. And if we have the domain triangles that sit on the sphere here, we could project them locally to tangent planes on the sphere. This is a projective map then, and use then affine maps, and everything boils down to actually, if we alternately optimize for the Bézier points, for the points of the triangulation on the sphere, and the affine maps, we also we get a linear optimization process here. Now, the nice thing about this, it doesn't work not only for the sphere, it works for any surface of any genus. So it would work for this double torus or similar surface like that. Why does it work? It follows from hyperbolic geometry, and I will convince you of it not using it by considering the following. If we have such a surface of genus gamma, we can cut it into either here a 4 gamma gon, which you see here. Here you see it again schematically. Or we can cut it into hexagons. These are what you see here is a pair of pens. There are 2 hexagons, one which you see here and one beneath. And that could either be closed by identifying these things, or we can stuck in further pair of pens, or you can split it into quads. And what we get then is either a quad mesh on that surface, or a hexagonal mesh, or a mesh consisting just of this one polygon. And these meshes have the property that all the nodes have the same valence. So then, since we are interested in triangles and transition maps, I can triangulate it further. So I have here green edges coming into in addition to these red edges we have here. And now we need transition maps going from these from one triangle to the next. And it's very simple to get them. Here they are. We have 2 transition maps, or 2 maps which we can use, this one for all the green edges and this one for all the red edges, and they would do the job. This has also been found by Jörg Peters for quad meshes, and then checked for valences up to 24. They derived it completely without hyperbolic geometry, even without homogeneous representations, purely algebraically, and it's amazing how they did it. And then they had to check it for each valence, so they had to stop at some point. But there's a nice proof of it, very simple. The compatibility condition here just means that we have to check this identity, Poincaré's identity. Going around a vertex, we have these alternating, these transition maps, and a vertex of valence nu means we have to do it nu times. So this needs to be the identity. And what we can do is we look at a very symmetric configuration of triangles, suitable here for this valence and so on, and then just read off the matrices. So I don't do it here, but this is fairly simple. And having these transition maps means we have parameter triangles in the parameter domain. And here I depicted it. They live in the hyperbolic plane in general. For torus, they live in an affine plane, and for a sphere in the elliptic plane. These are the exceptions. But otherwise, they live on the hyperbolic plane. What happens then is here, first we look at this torus. A torus can be parameterized over a square. And then I can go over the torus a second time. And that would mean I had another square here. I shift this square to a neighboring square that parameterizes the torus a second time. And since I can go over it infinitely often, I would then get shifts of this parameter domain that tessellate the complete plane. And the plane is then warped onto the torus infinitely often. Same happens here on the hyperbolic plane. Here's a fundamental domain that gets then infinitely often wrapped around that surface or shifted by hyperbolic translations, so to tessellate here the hyperbolic plane. Wow, this is known for a long time. I took it here deliberately from an old source, the book by Hilbert and Cohn-Vossen. So now we can triangulate this fundamental domain I constructed. I gave you 3 constructions of it arbitrarily. And from these triangulations then, or triangles, we then get transition maps that would do the job for our spherical, or in this case, manifold splines. And this has been used by several people, and I think this is a complete list in CHD to generate rational spline manifolds. But there's one more thing about it. We have here rational splines, and we can get integral splines if we consider the following. The transition maps we have here are such that the common boundary, the common edge of 2 triangles gets mapped onto itself identically. And that means that the ideal point of the line is mapped onto the ideal point. That means that parallel lines to this edge are mapped to parallel lines of that edge. And this basically means that the transition maps can be brought into the following form, where x is the variable running along this common edge, and the cross-boundary variable sits here in a projective map. Doesn't depend here, the second coordinate, on x, which means that if we differentiate that map here, we have integral cross-boundary derivatives, and if we use that in the usual CK constructions, we would end up getting integral splines, or we could end up getting integral splines. This has been used by Peters and his students in several papers. He, since he had a different approach of it, does it using making certain symmetry assumptions and so on. Therefore, he's restricted to special projective structures. In this paper here, the surfaces are only almost C1, and there are some singular edges where they are only continuous, but using what I had here before, you can also get C1 splines of it. I'm coming now to the last part of my talk, and I call it, it's the final destination, the super-spherical spline stuff story stop. Thank you for traveling along.
Thank you for your talk. Some question?
So the transition map you use means you have a symmetric gluing at each vertex.
Symmetric? No, they need.
Are the same.
No, the transition maps need not to be symmetric. There are 2 triangles that share an edge, and these triangles are arbitrary. I mean, it depends on what you do. I had to prove these transition maps. There I have a certain symmetry in it, yes. But this is only one particular example to show that it works. And then once I have this fundamental domain, I could take any other triangulation on it. So I'm not restricted.
So the transition is AB. So
yeah, it boils down to that I have 2 kinds of edges. Mm-hmm. And on the one kind, the green kind, I have one transition map that I can use for all these edges, and another one that I use for the other ones. Yeah, it's nice that it works, but this is one restriction. But then I could take an arbitrary triangulation and work with that. I can move the points in. Once I have it in the hyperbolic plane, I just move them. And then I have the triangles there, and I just one triangle and the next one triangle define the projective map, the transition map.
Okay. Another question?
you said that you can subdivide the surface into what are called pairs of planes. So, but why do you need general valence there? I mean, for that,
Well,
don't you just end up with valence 8 or 4? Or?
Well, if I do these pair of pens construction, I have valence 4.
Right.
But for the quads, I had valence 8. And for the other thing, I had valence 4 gamma. So therefore, just to be general, yeah, and I can construct a little bit more than what I showed here, I need other valences too. So I just did it for the general case.
Okay.
There's no, well, I have no example, or not for every valence I have an example for you. So,
But so
I do
what
more
is
than
gamma? So what is gamma? What?
Gamma is the genus.
Okay, thanks.
Okay. No question? So we can thank again our speaker.